Okay, hi. Today I'm going to explain things I've learned and explain the lab report, the last lab report. So, over the course of this lab, I explored four major areas in embedded and applied AI: TinyML, edge devices, prompt engineering, and computer vision. Each one brought different layers of understanding, not just theory but real hands-on experience, deploying AI in ways that are fast, lightweight, and practical. Let me walk you through exactly what I did in each section and how it worked and what I learned and how these systems can be applied for improving real-life scenarios. So first of all, it's TinyML. So TinyML was all about pushing the limits of how small and efficient machine learning can get. The goal here wasn't to build massive compute-heavy models, but to make models light enough to run on microcontrollers with barely any memories or processing powers. These are chips you'd find in low-cost battery-powered devices like wearable sensors or like so everything in this section was about making models compact, responsive, and deployable anywhere. The first tiny ML exercise I did focuses on gesture detection using an Arduino Nano 33BLE sense board. The board comes with built-in sensors, including an accelerometer, which I use to record motion patterns, and I train a machine learning model to recognize specific gesture, like waving or tilting the board in a particular way. The model was quantized and converted using TensorFlow Lite for microcontroller, then deployed to the board. It worked in real time. I could move the board and it works classified and it would classify the motion accurately. This showed me how we can embed intelligence into wearables or gesture-based control system. In practice, something like this could be used in fitness trackers or smart remotes that understand physical inputs instead of buttons. For the second exercise, I shifted to vibration detection. This task also used the accelerometer, but the idea was different. It was about detecting vibration patterns rather than deliberate gesture. I simulated different types of vibration, like shaking the board lightly or tapping it harder, and collected data. Then I trained a model to distinguish those patterns. When deployed, the board could tell what kind of vibration it was experiencing. This is something I immediately saw value in, especially for industrial settings. Think about machines in a factory. If a motor starts vibrating weirdly, a system like this could flag it instantly. Even without needing internet to improve this, I'd work on collecting vibration data from actual machineries and use frequency domain features like FFTs for higher accuracies. The final TinyML task was voice detection. I trained a model to recognize short voice commands, simple words like yes or no. The dataset came from pre-recorded voice sample, which I then used to train the compact neural networks. Once again, I quantized and deployed it into the Arduino board, which has a microphone. What amazed me was how the chip could actually recognize speech in real time without sending anything to the cloud. It made me realize how powerful even a low-power board can be when optimized correctly. This opened up all sorts of offline voice interface for applicants, toys, or accessibility tools. To make it more reliable in the real world, I trained the model with more accent, more background noises, and possibly add a woke word to reduce false positive. In short, TinyML taught me how to embed intelligence directly into smallest, most constant devices, and that kind of capability is the key to making the smart environment truly decentralized and responsive. The second topic I learned is edge devices. The edge device is part of the lab built on top of the TinyML, but with more computational power. Instead of using microcontrollers, we use devices like Raspberry Pi, still small and portable, but powerful enough to handle more complex tasks like object detection or video processing. The focus here was to run AI models locally without depending on cloud servers. That means better privacy, lower latency, and higher reliability in an environment where internet isn't always guaranteed. The first edge device assignment was custom object detection project. I created a dataset using RoboFlow, collecting images from 5 object classes, which each class is having at least 50 images. In total, that was 250 base images. I then associated to the dataset, train an object detection model using Google Colab, and exported it to the deployment. Exported it for deployment. This wasn't just a pre-trained model. I had to build and customize the dataset myself, which gave me insight into how data quality directly affects accuracy. Once trained, the model could recognize my chosen object effectively. This type of model would be perfect for inventory tracking, sorting system, or even educational toys. For next step, I would experiment with hardware accelerators like Coral TPU, or integrate it into a live Raspberry Pi camera system to see how it performs in real time. The second edge device task was much more applied. It involved human detection using Raspberry Pi, combined with line on the fly for real-time alerts. I used a pre-trained model to detect human presence through the Pi camera, and when a person was detected, the script would send a notification through the line messaging app. Setting up the model was straightforward, and integrating the message API took some debugging. Once set up, it worked, and I could walk in front of the camera and get a line alert on my phone seconds later. That's powerful. It's cheap. It's a cheap DIY security system, great for home automation or elderly care. If I wanted to scale this up, I'd add like face recognition, detection zones, or even tie it to IoT devices like light or locks. Performance wise, I also noticed that the Pi runs hot under load, so I'd recommend passive cooling or using the Pi 4 with heatsink. The edge computing showed me how to make AI practical, real time, and deployable without needing the cloud or expensive hardware. The third one is the prompt engineering. This section was a little different, different flavor of AI. Instead of working with sensors or hardware, prompt engineering was about language models and how to communicate with them effectively. Tools like ChatGPT are so powerful, but they only give good results if you know how to talk to them literally. In this lab, I tried out different types of prompt role-based instructions, step-by-step format, and debugging prompts. What I found was that how you phrase a question changes everything. For instance, when I asked for an explanation of code in basic way, the output was fine, but when I said explain this line by line like a programming tutor, I got way better details. This taught me that prompt should be context rich and specific. I also tried chaining prompt together, feeding the output of one prompt into another, which worked really well for multi-step tasks like generating a report summary and then turning it into slides. In real life, I see prompt engineering as a vital skill, especially in area like customer service bots, coding assistants, or automated tutoring platform. To take this further, I explored prompt template or few shots learning techniques to give the AI better example to mimic. It's not about the AI being smarter, it's about you being better guider. And the last one is the computer vision. The final section of the lab brought me back into hardware, software, and interfacing, but this time was with a focus on images and videos. I use mGuCV as a C wrapper for OpenCV instead of Visual Studio. Working in a window environment, the exercise combined camera control, UI development, and real-time image processing. The first computer vision the first computer vision exercise was about real-time webcam streaming. I built a UI in C using Windows Form, connected a USB webcam using mGuCV and Steam Video into an image block component. This taught me the basic of how to control camera feed in a C application and how to display a real-time frame smoothly. It worked really well after adjusting up some platform settings, switching to Time64 build. The setup is foundational, and it's what underlies things like zoom video filters or surveillance system. With more time, I could have added motion detection or face recognition right on top. The second task was about image capture and histogram visualization. I extended the previous app by adding buttons to capture snapshots and adjust camera parameters like brightness. I also use histogram box to show real-time histogram of the video feed. This was cool. The histogram gave me real feedback on how exposure and brightness were affecting the image. It reminded me of DSLR cameras and pro apps like Halit that shows histogram to help photographers shoot better. In industrial settings, this same concept is used to optimize lighting for inspection system. I'd improve this by adding automatic exposure correction based on histogram feedback. The final computer vision lab was image thresholding. I created a feature where user can load a static image into the application, and then this technique is super useful for segmenting object in images, like detecting coins, barcode, or shape in controlled lighting. I saw how effective thresholding is when lighting is good, when the lighting is good, but also how sensitive it is to change the brightness or shadow. That's why in real-world applications, adaptive thresholding methods like Otsu or Gaussian filters are often used. If I were building a coin sorter or a system scanner, this would be one of the first techniques I'd implement. Final thoughts: each section of this lab gave me something different. TinyML taught me to think small but smart. Each device showed me how to scale AI in a particular way, and prompt engineering sharpened how I interact with AI tools. And lastly, computer vision gave me the skill to build image-aware system from scratch. I didn't just learn theory; I built things that actually worked, and now I know that how to carry those tools into real-world solutions. Whether that smart applicants, voice control assistants, surveillance system, or embed AI apps. This lab brought AI down to earth and into my hands. That's it for the explanation video. Thank you very much for watching.